Hello and welcome. In this video we're going to talk about sets, and this is of course it's a very basic and fundamental initial tool we'll use to build a mathematics. So sets are really basic, and we can talk about first x. X is, we're going to say, is the definition is going to be our symbol for objects, for an object. Okay, so X is an object. Okay, and then I'm going to say A is our kind of proto symbol for a set. And the basic question about anything is that of set inclusion. Set inclusion. That is X in A or not? Okay, and so what we say, and this is our notation, we say X is in A. We use the symbol of the epsilon symbol, and that means in. Okay, and so this is our statement, X is in A. Alright, and of course the opposite of that symbol means that X is not in A. We put a cross through the epsilon like that to mean not in. Okay, so that's basically, I mean, that's all you can do with sets. And when it really comes down to it, we have objects and then you have sets. And a set is defined by what's inside of the set. So the basic question also, it's always a binary question, which is X in A or not? All right, and that is what forms sets. So it's always part of that, being included or not included in a set. And that's this fundamental idea. And in fact, from this, we can build a lot of mathematics. Okay, so so some more notation. So more notation, and that is brackets. So brackets. The idea we can say X is equal to essentially a set of objects X, and then I put that vertical sign here, and I put Q of X like that. Okay, and so what this is some sort of statement. A statement a statement about objects X that define membership. Okay, so and a basic example here is, I'm just going to give an example. Sometimes you can just give it explicitly. If you can actually write down a finite number of objects and say A, for example, is 1, 2, 3, and 4. The numbers 1, 2, 3, and 4. So that's an example of that. But we could have another example. We can say that B, and this is well, actually I'm going to put this down here. I say B is equal to the set objects that were in A, but subject to the condition that X is greater than 2. So right here, that statement there, that's our Q of X right there. And this is some conditioning statement. Of course, we can also write B then is just going to be equal to 3, 4. That's another way to write the same thing. But this is the way we can build one set B out of another set. So essentially, we can take some larger set A. It has more elements in it, and by using some condition Q, which in this case is going to be X greater than 2, we can build another set out of the previous set. So so usually it starts by some basic definition of the types of objects. And then Q is just extra conditions. extra conditions that are on the objects that define set membership. Again, the ultimate question involving sets is what objects are in the set or not. That's the only question there is. It's always going to be a binary question. Is it in or is it not? Okay, so that's a good way to think about this. Okay, of course. So let's go further with this this idea. And so so again, note multiple conditions Q1, Q2, Q3 could be involved in defining a set. Okay, so that's one thing to note. I'm going to put that in a bullet point. Another thing to note would be, of course, sets can, and be infinite. They can be infinite, and that could be countably infinite or uncountably infinite, and we'll elaborate on that later. They don't have to be finite. So there's a lot of details here that we're going to just gloss over, but I'm sure at this point you have a fairly good grasp of those sorts of things. Okay, so an example of an infinite set would be we'll say that C is all non-negative real numbers. So all negative, and we can write that as follows. We'll use our bracket notation. X is an element of the reals. That's the type of objects we're considering, subject to the condition that X is greater than 0. Okay, so that would be a way of writing that. And that is, of course, an example of an infinite set. In this case, it's uncountably infinite because there's no way we can order them in a way to count them all up in some sequential manner. All right. So the next notion we want to build for sets is the notion of equality. So equality, we say that A is equal to B. It means that if, or I should say, for all X in A, it implies, and we're going to use that symbol here, implies that X is also in B, and then conversely, I'm going to put this symbol now, and that means here for all. For all, that's another symbol that we're going to use a lot. So again, I'm using a lot of new notation here that we're going to keep using through the entire course here. So hopefully you'll get this. This implies that way, and it means whatever statement we put here, X is in A, also means X is in B. It means if this is true, then that is true. Okay, and that's for all X in A. All right, and so this is our symbol for all. And if X is an element of B, it implies then that X is an element of A. Okay. Another way to write this is rather than saying conversely and having another statement here. So we have sort of symmetric statements. X is in A implies X is in B. X is in B implies X is in A. We can also say that X is in A if and only if, and that's IFF here. That's our new statement. IFF, X is in B. That's another way we can write the same statement. And that means what this really is we can also write this double arrow. And these are equivalent symbols in this case. It just means that the implication goes both directions. It doesn't matter which order we put them in. Both are true simultaneously or not true simultaneously. Okay. All right, so those are some notations there. And we're getting the handle of this. And of course, this is all very elementary, kind of common sense stuff. But I think the real goal here is that we're really trying to just get a really firm grasp on the symbols that we're using here. The for all symbol, the implies symbol, the idea of making statements like this and connecting it together with these logical implementation or implication type symbols. And that I think is really the main objective here, is taking these elementary ideas and just applying notation to them so that we can be consistent, and then when we go forward, everything is going to be easier to understand. Okay, all right, the next concept then is going to be that of the subsets. Okay, and of course this is another elementary concept we're all familiar with. And first we're going to talk about a proper subset. We say that A is a proper subset of B if for all X in A it implies that X is also in B, but X is not equal to B. Okay. And that's very key. That's this side condition we have. Certainly, if they were equal, this statement would also be true. But that means there are some elements that are in B that are not in A. Okay. So also then there's the other symbol. Alternatively, we say that A is a improper subset if it is not known if A is equal to B or not. Okay, and that means that A could be equal to B, but we're just not sure. Okay, all right. So again, very standard notation, but I think we're just getting the handle of using these logical definitions, that when we say A is a subset of B, we mean this broader statement here. And we should be able to, every time you see that, quickly break down the statement into these more detailed statements, sort of unwrap this statement into a set of more specific statements that can help you analyze different sets. Okay, and again, I think that's the real skill we want to build here. Okay, and so let's give a really just quick example. Of course, we've had that example before. 1, 2, 3, 4. 4 numbers in A, and then B is equal to X being in A, subject to the condition that X is greater than 2. And that, of course, is equal to the following set, 3, 4. All right, and then we say, of course, that B is a proper subset of A. Okay, very straightforward stuff. Okay, and then now we're going to talk about two special sets. Now we're going to talk about another concept, and that's that of, draw a line through here, we'll talk about special sets. So there's some really special sets we want to do, and the first one is pretty straightforward. It's that of the empty set. And we give it the symbol, the 0 with a cross through it, and basically it means that it's the set in bracket notation. It's brackets with nothing in it, so the set has no objects. Okay, so there's no objects in that set. So that's a very special set that we have this very special symbol for. And of course, it's always true that the empty set is always a subset of any set in our and I should put an improper note because A itself could be the empty set. But in general, this is always going to be true. And then finally, there's this other thing which we're going to call the universal set. So what is the universal set? Sometimes this exists and sometimes it doesn't. But it's usually, and it really depends on context. But the idea, the universal set, we usually give the symbol capital X, and it is basically all allowable objects. All objects we can consider within a given context. And the idea here is, and we can give an example here, if X then is just the natural numbers, 1, 2, 3, 4, ... going up forever, okay, then that represents this big universal set of all allowable objects that are under consideration. Then of course A is going to always be a subset, a proper subset of the universal set, and B, from my previous examples, is always going to be a proper subset of X. And the idea here is the universal set just gives you basically the playing field on which to study smaller sets, like that of A or B, for instance, here. And the idea here with the universal set is it just gives you context. It's sort of the biggest thing around. It contains all the objects that are under consideration. Okay, and of course that's a nice thing to be able to do. Okay, finally, and we also want to talk now about intersection and union. And union. Okay, so intersection and union, and we give the intersection symbol, of course, is that upside down U, and union is is right side up big U. Okay, so these are the symbols, and one way you got to think about these symbols is they're actually binary operators. So you might be asking, what the heck is a binary operator? Binary operator, of course, it has to it accepts two sets. Say e.g. We have A and B, and produces. That produces a a resulting set. We'll call it C. Okay, so the idea here is with this symbol, of course, you're going to go A intersect B, all right, and that's going to equal some resulting set C. So again, you put in two sets right here, and you get an output set. So this works, of course, exactly like an addition or subtraction operator would on numbers. The idea, 1 plus 2 equals 3, and so on and so forth. And the same thing here. So let's actually define what this set is. What this means, I'm just going to put a single arrow there to basically just describe what it means. And actually, no, let's actually define it specifically. It's going to be the set of all objects that are in some context where X is an element of A, and that's very important. We're using and as a logical symbol, and X is an element of B. All right, so it has to be elements of both A and B. So set inclusion, it's conditioned on set inclusion for both A and B, and that forms my output. All right, so that's a very straightforward thing. And of course the union, A union B, that equals my new C. That's going to be defined as follows: set of objects such that, subject to the condition that if X is an element of A, or, and that's a different logical operator, X is an element of B. By definition, we know that A union B, so here's some sort of corollaries here. This implies, of course, that A union B is going to be a subset. Remember, this is a C here, not a subset symbol. I'll put little capitals there. All right, and this is a subset of A. Oops, sorry, wrong way around. I'll do a quick erase there. A intersect B is, of course, going to be a subset of A union B. Okay, all right, and that's pretty straightforward to see how that works. Okay, and now finally, let's go back to that discussion of. So now let's talk about complements. So complements. All right. So and that is the idea of if I say that if I have two sets, so take two sets, A and B. Okay. Now if I have the symbol now, I'm going to say that I'm going to call the set C to be defined as A not B, and that symbol there means not. And what that equals is then is the set of all objects X such that X is in A and that's my logical operator, X is not a member of B. Okay, so it works a little like set intersection. It's a different sort of operator, and that equals my new set C. I'll put capitals there. Okay, all right, and so so this is a pretty straightforward thing to a symbol we want to be able to use. And of course now, so we can give some examples of things like this. So let's just do a special example. So of course, again, let's go back to our simple example we've been using all along. 1, 2, 3, 4, and we have B is equal to 3, 4. And of course, A not B is going to be equal to everything that's in A but not in B, so that has to be equal to 1, 2. Okay, again, pretty common sense stuff. Okay, now let's go, of course, let's now look at universal sets. So let's go again to the case now where there is some large, super large set that contains all objects. All right, and so in this case, this universal set, we have a very special notation. If I say now, if I have a universal set, I say that X not A, I'm going to give this a very special symbol, and so this is A and B are both subsets of our universal set. And this is what I'm going to call, I'm going to give this a special notation, that's going to be called AC, and that means complement of A with respect to X, our universal set, the set that A and B are always subsets of. So again, if this is the largest allowable set of objects I'm willing to consider, the complement of any set will be everything that's in X but not in A. And so let's go to a simple example again. We'll take our example that X is equal to the natural numbers 1, 2, 3, 4, 5, on forever. That's an infinite set. Then, of course, and if A was just like before, 1, 2, 3, 4, just the set 1, 2, 3, 4, then of course A complement is going to be equal to the set of all objects X that are not in A, and that of course is going to be an infinite set that starts at 5, 6, 7, 8, and so on forever. Okay. Alright, so that of course is a nice complement, and this also implies there's a corollary here, of course, that A union the complement of A is always going to give us back the universal set, and that is what you call a fundamental identity. Alright, so there's always a way of splitting the universal set up, and so you can think of this as a way of splitting X into two pieces. Okay, all right. So we've done a lot of pretty straightforward examples here of how this works. So I want to then go over one more set of identities, and we can call this video done. And these are pretty useful identities to think. So some basic identities. Involving complements. And if I say, okay, again, if I take A not B, the set, and I union it with B, of course, I'm going to get what out of it? A union B. Does that make sense? So again, I'm going to put parentheses around that. Okay, so I take everything in A that's not in B, and I union it with things in B, and of course that should give me everything in A and also everything in B. Okay, that makes sense. And another pretty useful identity, if I take A not B, everything in A that's not in B, and I intersect it with B, of course I know this is always going to be nothing. Okay, that's going to be the empty set. Also, here's some more important identities. Okay, again, if A and B are subsets of some universal set, okay, and therefore I should say that the AC and BC are defined. If they're defined, then if I take the union of A and B, and if I take the complement of that, it's going to be the intersection of the complements. Okay, and likewise, if I have I'll call this one identity, and the second identity, 2, is going to be if I take the intersection of A and B, and then I take the complement of that, that is going to be the union of the complements. And to see this, you can use this sort of Venn diagram style picture to kind of get an idea of what this is. So if I take some set A, right, X is going to be everything in this plane. It's going to be all the points in this little rectangular plane. And that's my A. Let's say that is going to be my B. Now if I take the union of those two things, I'm going to get the set that looks like, I'm going to just shade it all in there. Looks like these two circles that are kind of partially occluding each other like that. Alright, and then what I'm going to do is I'm going to take the complement of that, which is take those two circles that are occluded, and again, the X is everything outside of that, and the complement of that, of course, is everything outside. Right, so this is sort of works as a visual proof, just to build some intuition here. All right. The question is then, okay, what if I do, now let's say, so that basically says, okay, if I take this set A union B and I look at this complement, I get that. So this should be then A intersect, A union B, the complement of A union B, all this stuff out here. Now let's do the opposite. If I have A, there's my A, and if I take its complement, and that's going to be everything outside. And now I'm going to intersect that with the complement of everything in B. So what I'm doing here, what I've done here is define this side of the equality, right? And now I'm going to take this, I'm going to define this equality here. And I'm going to see if they result in the same thing. And there's B right here. And I'm going to take everything outside of B, which would be the complement of B, everything there. And if I intersect them together, it's going to be all points that have both in common, which has to be equal to, of course, the same exact thing. Like that, it's going to be everything outside. So again, fairly straightforward, but we want to get used to using this notation and being very fluid with it. That's very important. I think it really speeds up our logical inferences if we're able to use this notation very cleanly and smoothly. And so anyway, I think we've done a lot of the definitions and given a lot of great examples. In the next video, we'll give some more examples and move on to ideas around functions. All right, thank you very much.